Welcome everybody to the talk. My name is Mike Price. I'm the CTO here at ZeroFOX, and I'll be co-presenting today with my colleague Matt Price. Just to get the question out of the way, no, we're not brothers. We just have the same awesome last name. So with that said, we'll be talking about playing offense and defense with deepfakes today. So let's go ahead and get started. In terms of an agenda, what we're going to cover today includes what a deepfake is, since it seems that there are a lot of varying definitions for deepfakes, why we think deepfakes are or may become a problem in the not too distant future. Then we'll cover some public examples of offensive use of deepfakes, so videos that are relevant to the offensive topic. And then we'll look at some research into how deepfakes can be used as part of an offensive sort of attack, so to speak. Then I'll turn it over to Matt, who will talk about solutions, or the solution space, so to speak, including some of the public research that's been done and that's out there, as well as some private research that Matt's done into deepfake detection as well. Then lastly, we'll mention a note about open sourcing the Deepstar tool at the end of the talk. So what a deepfake is. From a historical standpoint, deepfakes are a relatively new technology. They've really only been around for the last couple of years. The first example of deepfakes, more or less, came to light as the result of some research work that was done in June of 2016. This research work was known as face-to-face, and a video, for example, was released showing how researchers could control the facial expressions of well-known folks. And so in this particular example, if you were to go search YouTube for this, you'd see that there are some researchers that are able to control the facial expressions of George W. Bush. If we fast forward to the end of 2017, then we see that the deepfake subreddit was created, and this is really where the term deepfake originated from. And this is also where the first source code was made generally public and sort of easy to access for performing deepfakes and face swapping. A little bit later on, in early 2018, the original face swap code made it onto GitHub in the form of various repositories. And Fake App, which was a little bit more of a user-friendly app, was made public as well. And this is really when folks began to experiment with the creation of deepfakes, so just a little more than a year and a half ago. In April 2018, we saw a really interesting video created by comedian Jordan Peele in which Obama was deepfaked. And after this video, folks began to ask the question about what happens if we combine deepfaking with political figures, and folks began to ask the question of whether these videos could be used to cause, for example, some issues on the eve of an election. In the middle of last year, which is only about a year ago, then research papers began to emerge regarding detecting deepfakes. And just in the beginning portion of this year, we've seen deepfake videos that have combined both the video component as well as some fake audio, for example, in the case of the fake Mark Zuckerberg video that we saw in June. So a relatively new technology that's evolving rapidly. In terms of a definition, for this talk, I did want to keep it simple. So although the term deepfake is being used more or less for any kind of doctored video at this point, the original definition is the one that I'm using in the context of this presentation. And it really means for a video where you have one person in it, then the face from another person has been swapped onto the person in that video. So given two people in two different videos, swapping their faces is really what the term deepfake originally meant, and that's how I tend to think about it. There are, of course, variations on this theme. So you have traditional face swapping. You also have puppet mastering, where somebody who's creating the video has control over the person in the video, so to speak, kind of like the face-to-face work I mentioned earlier. And then you have lip syncing, which is a technique that allows for an original video to be modified mostly so that the mouth or the lips of the video are controlled by the person creating the video. And then finally, for this presentation, we limited its scope to video only, so there's not much research that we've done around audio yet, and we certainly look forward to getting to that in a future presentation. Okay, so why deepfakes are a problem? So we certainly think that deepfakes could become a problem in the future, so there's not a lot to show for deepfakes being used problematically right now, but there's a lot of risk related to deepfakes. So in our day-to-day, we see a lot of online content being used in a very demonstrable way to commit crime or to cause other issues. There's a lot of scammy content out there, a lot of content that's used to commit fraud. There have been very public examples of content being used to influence elections, and so this tends to be made up of things like text and images, and folks creating all of these fake pages and profiles out of this content in order to trick people into doing things that they shouldn't otherwise do. One thing that's really interesting about deepfaking right now is that it's kind of like the period of time before Photoshop, where if in the 1970s maybe you were to see a photo, you would probably have trusted what you were seeing because it wasn't possible to easily edit those photos. In a post-Photoshop world, most folks don't pay a lot of attention to fake photos because they suspect that they could be fake because the tools are widely available and the tactics are readily used. In the case of faking people in videos, it's been historically very difficult to do that, very costly to do that, and it's just now becoming easy to do. And so still there are many people that aren't familiar with these techniques and that haven't seen faked videos, and so fake people in videos. And so there's a sort of window of opportunity right now for folks to take advantage of this in terms of creating videos with people in them that have been faked and to use those to gain the trust of other people. So one of these common scenarios that's described is that if a convincing deepfake were created and dropped on the eve of an election, could it influence the election? I do certainly think that that's possible at this point in time. And the other interesting characteristic here is that the cost to develop that video would be low relative to its potential impact. So in terms of public examples of offensive use of deepfakes, there are thousands of known public deepfakes out there floating around. As far as we're able to tell, a substantial portion of them, if not the majority, are all associated with adult content, so to speak. So for the purposes of this presentation, we exclude adult content. Then we're really familiar with only a few hundred or several hundred deepfakes that are out there floating around in terms of building a data set that we can look at for offensive and defensive purposes. Of all the known public deepfakes that are out there, none of them have really been confirmed to be used in a malicious way. And so at this point in time, although the possibility exists to use these deepfakes in a malicious way, that hasn't really been done yet. Jordan Peele's video of Obama certainly serves as an example of what's possible. And there are many other proof of concept videos that give insight into other ways in which deepfakes might be used in a malicious manner. There was, of course, a video that was released most recently around related to Nancy Pelosi, in which she was speaking, and the video had been slowed down. Although this wasn't a deepfake, it was just a regular video edited with regular video editing tools. But the media, to some degree, characterized it as a deepfake. So it does speak a little bit to the possibilities of using video to influence public discourse, even when they aren't deepfakes, let alone actual deepfakes. One interesting recent development is that Symantec did report that they had observed actual cases of fake audio being used to commit CFO fraud against some CFOs at corporations. And so, although the information supporting these claims isn't completely public, if all of the facts around this are as reported, then this probably makes up the first case in which we've seen a crime committed leveraging AI-related tools sort of in the deepfake realm. So it certainly serves as an early indicator of things that we may see in the future. So now we'll take a quick look at some clips that give insight into the offensive use of deepfakes. The first clip is a few seconds of Jordan Peele's Barack Obama clip. The second clip is Argentina's president with Hitler's face deepfaked onto his face. And the third clip is a few seconds of the Nancy Pelosi video.
We're entering an era in which our enemies can make it look like anyone is saying anything at any point in time, even if they would never say those things.
Esta fórmula lo que le garantiza a los jubilados que durante los próximos años nunca más van a perder frente a saltos de inflación o disminución.
So in terms of our research into offensive use of deepfakes, the first thing that I'll talk about is some work that was done to learn in pretty fine-grained detail what the process looks like for creating a deepfake. And then we'll move on to looking at some videos that were created that show how deepfakes could be used in an offensive context. So from a theory standpoint, the process required to create a deepfake is essentially a four-step process. The goal at the outset is to identify, in terms of making the explanation simple, identifying two people that are present in two different videos, with the goal being to swap the face from person B onto the face of person A in those videos. So you can go to a content platform on the internet. You can download a couple of videos with person A and person B in them. Once you have those two videos on hand, you'll extract all the data that you need from those videos in step 2. in order to train up your face swapping algorithm in step 3 so that you can then convert a new video that contains person A in it in step 4, which is the conversion step. The result of step 4, the conversion step, is your deepfake video. And so we'll dive into each of those steps in a little bit of detail now. So from an extraction standpoint, if we have our videos A and B, the first thing we need to do is extract each frame of video from them. Then the second thing that we need to do is perform face detection on them. And so we can use an algorithm like MTCNN or some other face detection algorithm to identify the presence of a face in each frame of video from each of our videos A and B. Oftentimes those videos will be unaligned, so they'll be rotated, for example. We need to detect the fact that they're unaligned and then perform a transformation on them to align them so that the faces are aligned prior to the training step, which comes next. And so an example of what that might look like a little bit more visually, imagine that in this slide you have a video. You then extract each frame of the video. You then perform face detection on the video. You might have some faces that are unaligned, and so you'll need to align them, which makes each of the faces aligned horizontally. And then suppose that you have video B. Then you have several frames of video for video B. You perform the same step for face detection, the same step for alignment. And at the end of this process, you end up with two groups or sets of images, group A and group B. And in both of these groups of images, you'll have multiple faces that correspond to person A and person B. These are the images that are needed as inputs into the training step. So from a training standpoint then, there is more than one deep learning algorithm that's used currently to create deepfakes. The original algorithm that was published on the deepfake subreddit leverages something known as an AutoEncoder. So the way that an AutoEncoder works at the high level is that you have some input, and then you have two models, an encoder and a decoder. You supply input to the encoder, and the encoder produces a compressed version of its input, so something that contains a little bit less information than the original input. This compressed version of the input, known also as latent image, is then supplied to the decoder, and the decoder's job is essentially to try to recreate the original input that was supplied to the encoder. Now, all the different faces that are extracted from the frames of video are supplied to this network, and the training process causes the encoding step and the decoding step to improve over time until the results that are produced by the decoder are sufficiently similar to the original input to the encoder. And this is how the AutoEncoder is trained up. And so if we look at this visually, then you'll see that there's a picture that's input into the encoder, a modified version that is produced by the encoder and passed along to the decoder, and then a sort of lossy image that's produced by the decoder. This just represents the AutoEncoder process from start to finish. In the training step that's used by the actual face swap algorithm, a little bit of an architecture, different architecture is used than the traditional AutoEncoder. So in this case, we have one encoder that's used, but we have two separate decoders that are used that each correspond to video A and video B, or to the two sets of face images, extracted face images. So in this case, then, we take an extracted face from video A and extracted face from video B. We supply to the encoder. The encoder produces two latent images, and those latent images are then supplied to their respective decoders. From this point, then, the recreated images are produced by the decoders, and the same measurement of loss is performed, and the training process continues until the outputs from decoder A and decoder B are sufficiently good. And so by performing this process, then, the models are able to learn the important characteristics of each of the faces in image A and image B. And by splitting the decoders in this way, it makes the conversion process more possible, as we'll see in an upcoming step. So here, from a visual standpoint, then, we can see two extracted face images being supplied to the encoder with their resultant latent images being produced and supplied to the corresponding decoders, and then the lossy images come out. This process would again be repeated as part of the training process. We can take an even more detailed look. Overall, this is the same process as was described in the last slide, but with some of the intervening steps highlighted in further detail. So long story short, the images fly through, although some of the training data is modified as part of the actual face swap algorithm. And then we're able to use a feature of Caris that allows us, Caris, which is a machine learning framework, that allows us to export the deep learning networks that are used for the encoder and the decoder as PNGs, and so we can explore what those actual networks look like in detail. So here we see a high-level view of the encoder and decoder. Here we see what the actual network looks like for the encoder with all of its different layers and characteristics. Here we see what the network looks like for the decoder with all of its layers and its resulting characteristics. And if we move past the training step then onto the conversion step, we can see that in order to finally create the deepfake from our trained models, what we'll do is we'll find a new video C that contains the same person that was in video A at the start of the process. So it's a new video, but with the same person. We'll extract each frame of video from video C. We'll perform our face detection and our alignment again from that video C. And then in this case, we'll take all of the faces that we extracted from video C and we'll supply them to decoder B. So this is really more or less where the magic happens. So it's important to note that in this case, what we're doing is taking extracted faces that contain the face of person A and supplying them to decoder B, which has been trained on faces for person B. And so this is the step at which the transformation occurs, where the face for person B is then face swapped onto the face for person A. And then that resulting image is output from decoder B, passed along to the transformation function that aligns that face back to the original alignment of the face. And then all of those frames that are produced by this process are compressed back into video D, which is the deepfake. And so to display that visually then, we can see the same process, but with just some pictures in place. And so you can see that the face from person A is applied to the encoder, which produces the latent image, which is applied to the decoder for person B, which produces, roughly speaking, the sum of the two faces, which you can see here in terms of images, or we can represent it even more visually in the slide here. So then after having dug into how the face swapping algorithm works in low-level detail, I wanted to dig further into creating some example videos. I wanted to look at something that would reflect sort of the concerns around election meddling. And so what I chose to do was to create a mouth swap video in which Representative Adam Schiff, who's a member of the House of Representatives in Congress, would essentially be speaking, but his mouth would be replaced by my mouth, which would have been extracted from a deepfake that I created. And so the process, very simply put, is I took a video of Representative Adam Schiff from an online provider. I created a video of myself. I face swapped Adam Schiff's face onto mine. I then performed mouth detection and extraction on that resultant deepfake video to extract just the mouth from that video. And then I overlaid the extracted mouth or the frames of video containing the extracted mouth onto the original Adam Schiff video. And so the idea being that I could essentially retain the original Adam Schiff video, but with my mouth swapped onto his. And then, of course, there are a lot of little details in that process, such as performing color correction on the mouth that's overlaid, doing some different things to be able to blend that mouth onto Adam Schiff and to manage the location of that mouth over several frames of video, for example. So in terms of tangible examples of videos that could be used in an offensive context, I did create several videos, which I'll show you now. The face swapped deepfake that was used as the first step in performing the mouth swap was created with the face swap utility that's available on GitHub, so something that the face swap folks had created. And then the rest of the operations that were required to create these videos were created with Deepstar, which is a tool that we created as part of the research supporting this presentation. The operations that Deepstar handled included pulling the video that was needed to train face swap, pulling video needed to prepare stock footage, all of the video editing operations. So this was done from the command line, basically, merging in of the deepfake into the larger or the broader video, as well as the application of the mouth swap effect and deployment via email and SMS were all performed by the Deepstar tool. And so the first video that was created was essentially just this video of Adam Schiff talking. So this is an actual video, but with the mouth swapped over him. And so you can see somewhat what the results look like from this video. Now, in the next slide, to take it a step further then, what I chose to do was to edit the deepfake of Adam Schiff into a fake Fox News segment, just to give a sense for how you might bundle up a deepfake and deploy it. Although in this particular slide, it's just a little bit of comedic relief because it's talking about the representative's love for puppies. repeated this process for CNN, and so I created a fake fake CNN news segment containing also Representative Adam Schiff saying the same thing, declaring his love for puppies. Then I repeated this process yet again for MSNBC. And the point of creating the multiple different videos was really to show that you could use this technique to take a deepfake, control the mouth, so to speak, weave it into a news segment, maybe from any different news channel, whether domestic or foreign, and then you could begin the process of distributing this content. Once I'd created the videos, then I used the tool to deploy those videos via email. So I took a template, I populated the template with the URL to the videos, and then I sent these videos out via email to a set of test email addresses, so email addresses that belong to me. And then I performed the same operation via SMS. And so my interest was in demonstrating how you could go from the deepfake to the produced video to uploading it to a content platform to distribution via email and SMS as a sort of end-to-end demonstration of the kind of thing that you could do to, for example, influence an election, considering the timing. And then finally, the more malicious video, which essentially depicts something a little bit more nefarious that could be done, is where the same video is used, but in this case, Representative Adam Schiff is declaring that Donald Trump has been exonerated of all charges related to Russia. Of course, this is not a real news clip, but if it were distributed in the way that I have described, then it might influence opinions. And if it were done with the right timing, then it might actually impact bigger, broader issues, public discourse, and things like that. So otherwise, I had intended to distribute these videos in the wild and to measure their impact. However, as development of the talk proceeded and as everything became a little bit more real, based on some internal discussions and reflection, the decision was made not to circulate the videos in the wild at this time. And so that's something that we'll have to give some consideration to and look into doing in the future. And finally, from a results standpoint then, on the offense side, really what I was interested in exploring was kind of what's been done on the offensive front. What are some of the possibilities? How could you go from deepfake to actual content delivered to a person where you're actually making an impact with respect to that person? The end-to-end sort of process hasn't been explored until now. I do think that this process can essentially be used to produce end-to-end automated deepfakes that are delivered to folks for doing things like influencing elections. And the question that I really have is if more effort were put into this, if somebody else created a higher quality video and timed it in a very specific way, could they influence an election? Would we be ready to stop it? And I think that the answer is probably no, which is really ultimately the point of this research and this presentation. So with that said, then I'll turn it over to my colleague Matt to talk about the detection side of the equation.
Hey everyone, I'm Matt Price. I'm a principal research engineer here at ZeroFOX. And now that Mike has kind of gone through how we can create deepfakes and how we can use them offensively, now I'm going to switch gears and have us talk about how we can detect deepfakes. So the first point I want to make is that humans are not very good at detecting image manipulation. In a study done by European researchers on 143 computer science students, they showed them a mix of images where 50% of the images were pristine or real images, and the other 50% had been generated using 3 different types of deepfaking algorithms. In this instance, what we ended up finding is that at best, the students are able to detect real images at a rate of about 80%. When we start talking about images that have been manipulated, however, the best rate at which the students are able to accurately detect that these images had been manipulated was 75%, and at worst, 40%. So what this study tells us is that, unfortunately, even if we had the capability, an army of humans is not going to solve our deepfake problem. Luckily, there are a number of existing methodologies and new methodologies that are emerging for detecting deepfakes. One of those methodologies deals with looking at images at the signal level. So this is looking at things such as sensor noise, double JPEG compression, artifacts left behind by the AutoEncoder, for example. Another way of detecting deepfakes is at the physical level. So this is looking at things such as lighting conditions and shadows. So for example, if a light source in a video seems like it's coming from the right, but all of the other objects in the video indicate that the light source is on the left, That's a red flag that the image has most likely been manipulated in some way. Another way of detecting deepfakes is at the semantic level, and this is really checking the consistency of the metadata around the video. So for example, if someone releases a deepfake of a public figure and they claim that this public figure was at a certain location at a certain time, we can go back and verify that indeed that public figure was in this location on that date. So those three methods that I just spoke to, the signal, physical, and semantic level methodologies, these are methods that have existed in traditional image forensics and are now being applied towards detecting deepfakes. A new methodology that has recently emerged that is unique to detecting deepfakes is using humans' physiological signals. So things such as breathing, eye blinking, facial orientation, and so on. What's interesting about physiological signals is that they can be tailored to the individual or they can be generalized, so they work across any number of individuals. Two other methods that I don't really consider to be detection methods, but are at least worth mentioning, are video authentication and black and white listing. Both of these methods really deal with providing trust that if you're looking at an image or a video or even listening to audio, that the source that produced these things is indeed a trusted source. So for example, it could come from a trusted individual or it could come from a trusted organization. So now that we've talked at a high level about the different methodologies that exist for detecting deepfakes, let's actually talk about some of the implementations that have been released. One of the things I do want to note is that detecting deepfakes is a relatively new area of research, with any published research only first starting to emerge in the summer of 2018. So this is very much a new and open area of research currently. One of the first methods that was published for detecting deepfakes dealt with eye blinking. So the reason that you could detect deepfakes using eye blinking is that eye blinking is a human physiological trait. And when you start manipulating video, for example, creating deepfakes, what was happening is that the frequency at which one blinks was altered. So researchers noticed this, and what they noticed is that in deepfakes, the target almost never blinked. So they trained up a neural network image classifier to simply classify in a video frame whether or not an individual had their eyes open or closed. They then ran this over a series of video frames, and based on the number of detections they got for eyes being closed, the researchers were then able to determine whether or not the video was a deepfake. So unfortunately, while this method did have a high rate of accuracy and was working quite well, less than 2 weeks later, a researcher working on the offensive side and creating deepfakes realized the way to get around this model. The solution in this case was simply to make sure that you included in your training set for your deepfake algorithm enough images of your source with their eyes closed. Another way of detecting deepfakes, in particular at the signal level, deals with the photo response non-uniformity pattern, or PRNU pattern. The PMU pattern is a new method that's actually used in traditional image forensics that came out about 2 years ago. But what's unique about the PMU pattern is that it's referred to as the digital fingerprint of a camera. And the reason that's referred to as a digital fingerprint of the camera is that when the light sensors on the camera for a camera are produced, there are factory defects that are unique to each and every sensor. These defects in the light sensors you can actually capture and measure in the video. So when you start manipulating video frames, for example, you destroy that PRNU pattern. So what these researchers did is they went and extracted faces out of a sequence of video frames, broke those into 8 uniform groups, and then computed the average PRNU pattern for each of those 8 groups. They then took the mean normalized cross-correlation score between all these groups, and that's what you can see plotted here on the slide to the right. So in this case, as you can see, for authentic videos, there's a high correlation across the PRNU patterns. While for deepfakes, again, that PRNU pattern is getting disrupted, so we can detect that those videos have indeed been manipulated using the PRNU pattern. The one downside to this detection method is that oftentimes videos can be shot from multiple camera angles, so you have multiple cameras producing multiple PRNU patterns, and this can throw a lot of false positives. Another way of detecting deepfakes is using novel neural network architectures. A really interesting one is called Mesonet. So with Mesonet, what the researchers hypothesized that at a microscopic level, which is the level that complex convolutional neural networks work at, you end up losing too much information because as the image size starts to degrade or become smaller throughout the convolutional layers, you've lost that information. So that's working at the microscopic level. On the other hand, working at a high level, at a macroscopic level, which is the level that humans work at, you have too much information and you can't determine whether or not an image has been manipulated. So therefore, a neural network that operates in between both of those levels at the mesoscopic level will produce the best detections. So to test this hypothesis, what these researchers did is they started with a very complex convolutional neural network and bit by bit removed layers until they ended up with the model with the smallest amount of layers that did not sacrifice any accuracy. The ultimate result was a 4-layer convolutional neural network that does have rather high results in terms of its accuracy on deepfakes. Another interesting neural network architecture that's at least worth mentioning is the capsule forensics network. So in this case, what the researchers did is they used VGG19, which is a very popular image classifier, as their backbone. And they fed those outputs from that image classifier neural network into 3 primary capsules. These 3 primary capsules in and of themselves are each small convolutional neural networks, and they are each trained independently, so they learn different features. These features are then dynamically routed to 2 output capsules, a real image capsule and a fake image capsule, at which point you can then make a determination if the video is a deepfake or not. Another class of neural networks that's actually very well suited to solving the deepfake problem are recurrent neural networks. So the reason that recurrent neural networks are extremely useful in detecting deepfakes is that we can actually measure temporal differences using recurrent neural networks, specifically using long short-term memory, or LSTM. And the reason that it's important to track temporal information is that the autoencoder within the deepfake generation process only works frame by frame. So what this means is that the autoencoder is unaware of previous faces that it may have generated, it's unaware of previous scene information, and it's really not even aware of the scene information that's trying to insert the face into. This can lead to a number of temporal discrepancies, which is what we're trying to exploit with the RNN and tracking intraframe differences over time. Another interesting extension to this, what I would call a kind of traditional RNN model, is using forgery detection methods and actually feeding that time series information into a recurrent neural network. So what these researchers did is they took traditional image forgery detection tools, ran those over a video frame, and then fed that into the neural network. They then repeated that over a series of video frames, and over time, the temporal differences between these forgery detection tools can indicate whether or not the video is a deepfake. Another method for detecting deepfakes, and in my opinion one of the more clever ones, deals with head poses, specifically facial orientation. So the insight here from these researchers was that when you actually generate the deepfake, when you actually replace someone's face, you disrupt the central facial landmarks, and this will cause a mismatch in the estimated orientation of one's face. So what these researchers did is they took an estimate of your head orientation using just your central facial landmarks, so your eyes, your nose, and your mouth. They went and then took another estimate of your facial orientation using not just your central face landmarks, but also your chin, your cheekbones, and your forehead. So, and based on those 2 estimates, the researchers were then able to determine the video as a deepfake. And the reason for that is that if the facial orientation matched across both those estimates, then more than likely that was a real video. If there was a significant difference in the estimate, then most likely that video had been manipulated and we're looking at a deepfake. Another way of detecting deepfakes at the signal level is looking at face warping artifacts. And really what I mean here is that we're looking for evidence of any kind of affine transformations that may have been done as you map the face from the source to the target. So affine transformations are things like scaling, rotation, shearing, and so on. And as an image goes through this process, there are traces left behind that, for example, scaling did occur and that bilinear interpolation was used. We can train neural networks, for example, to detect the presence of these affine transformations. Another way of detecting deepfakes is actually looking at how internally the deepfake generation process works. So within the deepfake generation process, there is a generative adversarial network, or a GAN. And what's unique about these GANs is that internally the weights for the GAN have to be constrained. And the reason for this is that we can't allow for an explosion of pixel values. Pixel values have to be between 0 and 255. So because of this, what actually ends up happening more often than not is that the GAN's weights follow some sort of uniform distribution. This is actually reflected in the pixel values that you see in the image. So, for example, if you end up seeing a roughly uniform distribution of pixel values, there's a good chance that that image is actually indeed a deepfake, because in real life, colors don't follow a uniform distribution. And you can actually see these idea visibly in both of those graphics on the right part of the slide. Ultimately, what these researchers did is they measured relative pixel frequencies within video frames, and based on those relative pixel frequencies, the researchers were able to make a fairly accurate detection whether or not a video was a deepfake. So on this slide, there's a lot of information, but there's really a couple of things that I want you to take away from this. One is that all of the models most of the models that I've talked to were all tested on a common data set. So this allows us to kind of do an apple-to-apples comparison of how each of these models worked. As you can see, whenever we have access to the actual raw video footage, so before any kind of compression or changes in video resolution have been done, almost all of the methods I've talked to are fairly accurate. Very close to 99% accuracy rate for most of these models. On the other hand, as we start degrading the video quality, so in this case, what the researchers did is they degraded video quality by compressing it, you can see that the accuracy of these models declines. The other thing that I want to point out is not only is the accuracy declining as you drop the quality of the video, but across the board, all of the models are getting about the accuracy of a human. So one of the things that really has to be addressed moving forward is how do we develop these models that work on both high quality and low quality video. So all the methods that I've talked to all the implementations that I've talked to up till now deal with generalized detection methods. This next method that I'm about to talk to is actually tailored to individuals. What these researchers did is they discovered that people have very distinct facial and head movements. And when you create a deepfake, these head and facial movements tend to get disrupted. So what the researchers did is they took a 10-second clip from a video, and from that clip, they're able to extract 190 different individual features. They then used a sliding window of 5 seconds and ran this sliding window across the length of the video and produced a number of feature vectors. These feature vectors, when mapped out to two-dimensional space, you can actually see here on the graphic to the right. And what I want to bring your attention to in particular are those gray dots kind of towards the bottom right. Those gray dots represent a real video of President Obama. On the other hand, the black dots that are kind of surrounding those gray dots on the further to the right are of a lip sync deepfake of President Barack Obama. So as you can see, there are definite differences between the deepfaked President Obama and the real President Obama, which is part of the reason why this method works. The other thing that's really nice about this method is that the researchers used a support vector machine. So because they used a support vector machine and giving the type of features that they're providing to this model, the training data only requires real videos of an individual. All of the other methods I talked to prior to this require you to either find or create deepfakes and include those as part of your training set along with real videos. The fact that you only need to gather real videos for this model is a real boon because it's a lot easier to find real videos right now than it is to find examples of deepfakes. So despite the progress that's been made in the past really year and a half, there's still a number of open detection method issues. Two of these I've already talked to, but video compression resolution continue to be a problem. Another major issue is that there's a rapid improvement in deepfake generation capabilities. Even within just the past couple of months, we've seen some really seminal developments in deepfake creation and detection. On the detection side, we have to keep up with this rapid improvement cycle. Another issue is that currently, none of the models that I've talked to have the ability to detect all three types of deepfaking methods. As Mike mentioned earlier in the presentation, there's three types of deepfakes, or deepfakes can be created in three types of ways. There's the lip sync model, there's the puppet master model, and then there's the face swap model. All the models, all of the detection methods I've talked to tend to work fairly well for face swap, somewhat okay for the puppet master, but most of them do not work for the lip syncing deepfakes. So because of this, creating one model to detect all three deepfake methods is a critical development in our detection capabilities. Another issue is what I call selective deepfaking. This is, for example, when only small portions of the video have been deepfaked. So maybe you have a 5-second long video, only 30 seconds of that video have actually been manipulated. Another issue with selective deepfaking is when you have multiple people in a video and only one or a few of the individuals have been deepfaked while the rest continue to be unmanipulated. So now that we've talked about some of the public research that has been done, we've been doing our own research in the deepfakes for about the past year. And one of the things I wanted to share with you today is our research that we did into creating a single model that can detect all three types of deepfakes. So I call this model MouthNet, and that'll become apparent why here in the next minute or two. So to start off with, this is an image classifier, and for its backbone, we're using the latest version of the Exception ResNet model. And then on top of that, we add 2 additional dense layers. So the model itself is not very unique, but what is unique is what we feed into this model. So all the other models that I've talked to prior to this, they all extract the face and usually provide that as an input to the model. What we decided to do was to extract just the individual's mouth and provide that as input to our model. The reason that we're using the mouth instead of the entire face is that all three types of deepfake methods have to touch the mouth by definition. However, all three types of deepfakes may not necessarily touch the entire face. For example, with lip syncing, which is kind of the lowest common denominator here, only the mouth is altered. The nose, the eyes, and other facial regions are not touched. So what our hope was is that by isolating the area that was definitely going to be changed by all the deepfake methods, we'd then be able to detect across all of them. One of the other things that I do want to mention is that we limited our videos to online platforms and did not go online content hosting platforms. It did not, for this model anyway, gather any models that were, or any videos that were available on the deep or dark web. In terms of our training set, we had about 200 videos. For our validation set, we had 50. Then for our test set, we had 100 videos. One of the things I do want to mention is that our validation and test sets contain videos that the model has never seen before. So the accuracy in our validation test sets should give us a fairly decent idea how well our model will generalize to unseen data. So before I show you the results of the model, I want to give you a little bit more intuition as to why MouthNet should work. Here you can see 2 pairs of images that I've extracted from 2 different videos. So what I've done here is I've held video quality constant. Just looking at these images, you can probably tell there are visible differences between the fake and the real mouths. For example, with the fake mouths, the teeth tend to be all connected. You don't really see the gaps, and they also tend to be fairly flat. Most people don't have perfect teeth, so it's very unlikely in any kind of real video you're going to see teeth like this. The other thing that I want to mention is, besides having the model actually visibly detect these differences between real and fake mouths, I was hoping that it would also pick up on some of the artifacts left behind as part of the affine transformation process that the mouth has to go through as it gets mapped from the source to the target. So here are the results from MouthNet. The first thing I want to point out is the image classification validation accuracy, which was 83%. I'm actually fairly happy with this accuracy, mostly because, one, I did not make any kind of distinction in the training or validation or test sets as to video quality. So there's a mix of video quality within these data sets. The second thing that I want to mention is that we are trying to detect all 3 types of deepfakes. Because of this, this is a very difficult problem, so to get an accuracy of 83%, I'm very happy. I'm happy with right now. One thing I do want to note is that we did implement Mesonet as a baseline model, and on that same data set using faces instead of mouths, though, it had an accuracy rate of 72%. So you can see by the model that we have developed seems to have a significant boost to its accuracy compared to at least Mesonet. The other thing I want to mention is that both Mesonet and MouthNet were overfitting. You can see this in the validation curve on the right. Because we are overfitting, what I suspect is that we need to collect more data. Specifically, we need to collect more examples of the puppet master method and the lip syncing method of deepfakes. Face swap tends to be fairly easy to find on public platforms, but the other two methods are much harder to find. I believe more samples of those are needed to help deal with this overfitting problem that the model is encountering. So in terms of the test results in the 100 videos, I used a very simple detection method for this. What we did is we extracted the first 100 frames that contained faces, and then we averaged the predictions of the model over a predefined threshold that we determined. And if the average of those predictions was greater than the threshold, then we had a deepfake. So in this case, for this version of MouthNet, I used a threshold of 0.9. And using this threshold, we successfully detected 41% of the deepfakes and misclassified only 10% of the real videos. So while we are missing deepfakes, we can see that we are making some substantial progress towards actually detecting deepfakes accurately without too many false positives. One other area of research that I looked into was, are the convolutional neural networks that we're creating to detect deepfakes actually scale invariant? There's been emerging research recently done that convolutional neural networks are not always scale invariant, and it depends on the problem that you're working on, which is part of the reason why we have ideas like progressive resizing starting to enter into popularity these days. So what I did is I created 4 different image buckets. So you can see those buckets here on the slide. So 60 to 89, 90 to 119, 120 to 149, and 150 to 108 pixels. For each of these buckets I created for the mouth sizes, I then trained 4 different MouthNet models on each of those. So you can see their classification accuracies there. As you can see, we are getting a fairly sizable bump in our accuracy simply by taking into account the image size. The one thing I do want to note is that the bucket from 150 to 180 pixels, the reason that that accuracy actually kind of dropped was that was the bucket that we had by far the least amount of training samples available for. So because of that, I think that accounts really for the drop in accuracy for that image bucket. In terms of the test results on 100 videos running this kind of bucketed MouthNet, we used a threshold of 0.5. You can see that we detected 53% of the deepfakes. However, we also had a bump in the number of real videos that we misclassified. Unfortunately, it went up to 26%. So while we did get a bump in deepfake detection, we also got a bump in our false positive rate as well. The last thing that I want to bring your attention to are the model accuracies on the test videos. And that you can see over in the bottom right of the slide. Here you can see our baseline model, the gray line, which is Mesonet. And above that, substantially above that, are both instances of the MouthNet model. You can see that the MouthNet model that takes into account the image buckets, it does have a slightly higher accuracy than the original MouthNet that did not take into account image size. However, it remains to be determined after we add additional training data whether or not that difference in accuracies continues to increase or if we don't see really any kind of bump in accuracy. One of the things that I did is I went through and looked at the videos that all the models had misclassified and tried to see if there are any kind of trends. And these are the results that I found. I've already mentioned this quite a bit, and we're seeing it still here, is that low resolution videos are causing a problem for the models. One of the things that we're starting to do moving forward is that not only are we retrieving the high quality versions of videos, we're also retrieving the lowest quality version of that video as well. So I'm hoping by growing our data set with more examples of low resolution videos that we will hopefully solve this low resolution problem that a lot of the models are encountering. Another issue, and this kind of just shows you that when you start running models out in the wild, you never know what to expect, is that the model was continually misclassifying movie trailers and baby videos. I suspect actually that movie trailers are digitally altered, which the model is picking up on. And because of this, the model is actually classifying movie trailers as deepfakes. One of the things I really did not expect, but obviously quite a few people post videos of their babies onto content hosting platforms. I only included one baby video within the training set, and because of that, the model was really unable to determine one way or another what to do with baby faces. So really moving forward, I need to make sure that I do include examples of baby faces within the data set. Another issue obviously is selective deepfaking, in particular having multiple people within a deepfake. And in this instance, I think one of the things I need to do is cluster faces by similarity and then run our models over those clustered faces, and really then determine whether or not the model is the video is a deepfake. And finally, the last thing is face extraction. The better the facial extraction model that you're using, the better that your deepfake model is going to perform. I've noticed that in certain videos, the facial detection model that we're using, MTCNN, was actually generating a lot of noise. And because of that, certain videos were misclassified simply because the deepfake detection model, MouthNet, didn't know what to do with that noise. So before we wrap this up, one of the things I wanted to do was introduce a tool that Mike and I have developed called Deepstar. So we built Deepstar because we noticed that there really wasn't any kind of tooling available that really streamlined deepfake detection research. There were a lot of tools obviously available that had streamlined deepfake creation, but not the defense side. So we found it really useful for curating our data sets, and as well as just testing some of the new detection algorithms that we've been coming out with. You'll be able to find Deepstar available at ZeroFOX-OSS, which is ZeroFOX open source organization on GitHub. So please take a look and make contributions back if you find it useful. And with that, I'd like to thank everyone for listening to our talk on deepfakes, and good luck detecting them.